So we are ready. Welcome everybody and good afternoon. My name is Lars Petter Malpi. I'm the CTO of the ID cluster and I'm also the project manager for the BATMAN project. So we have decided in the BATMAN consortium that we are arranging a series of short webinars to give insights into the various working packages. So previously on Thursday, April the 29th, we addressed the EU battery regulation proposal and how to discuss its implications for Norway. Today we are addressing a status update on the lithium-ion battery technologies, which will be addressed by Hanne Flåten Andersen, Head of Department for the Battery Technology at the Institute of Energy Technology. And then Erik Figgenbaum will give us an update on the electrification on the road transport in Norway. So Erik is the Chief Research Engineer at the Institute of Transport Economics. So we are planning now, following each other, two 20-minute presentations, followed by approximately 15 minutes of a Q&A session. So you are all welcome to use the chat function to ask questions or to simply add a comment in the chat so that others can read and take a note of it. So there are two functions in Zoom. It's a Q&A and chat. So we ask you to ask your questions in the chat functions. And please also note that this event is recorded. So with that, just as a background of what you see on the screen today, the BATMAN consortium is consisting of key companies in the battery value chain and also key R&D actors related to the BATMAN. And BATMAN is abbreviation or a very long name, which I will not read out loud, that you can see in the top. But it basically gives us the Norwegian possibilities within the battery value chain. So with that, I think we should start the presentations, and I will stop sharing my screen and give the floor to Hanne, which will present on the update on the lithium-ion battery technologies.
Thank you, Lars Petter. I will see if I can share my screen then. Get in presentation mode.
You are good to go.
Good to go. Thank you. Thank you for the introduction. As mentioned, I will present the current and future trends within the lithium-ion battery chemistry. But first, I want to just say a few words about the IFE, my place of work. We are Institute for Energy Technology, a non-profit organization. We're located in Kjeller, where this aerial picture is from, and also in Halden. And we are doing research on a lot of various energy topics. And I'm heading the battery technology department at IFE. We are quite a large research group now working on batteries for more than 10 years. And we are covering a broad range of topics on the battery value chain, but we have been specializing within the silicon-based materials as an anode material, also general materials and cell development, and also testing at the R&D scale, and also lifetime and degradation testing of commercial battery cells. Lars Petter now also introduced the BATMAN project, which we are a part of. So I won't say the very long title either. But the main goal of the project is to make it possible for the Norwegian companies to take leading positions in the rapidly growing battery market. And we are doing that by developing a predictive model that defines the demand for materials and also looking at the secondary use and the recycling volumes, which can then in turn be used as a strategic tool for the industry. And we at IFE, we are responsible for giving input to this model by delivering a scientific report on the lithium-ion battery technology mapping. And looking at different reports that give different outlooks for the global battery demand of the future. They all agree on one thing, and that is that we're seeing an almost exponential growth in the years towards 2030. We have a figure here that is, let's see if I can release Figure here showing the different segments towards 2030. So we see a large increase in the passenger vehicle side. Also expecting an increase on the commercial vehicle side, but also stationary storage will see an increase and use in the future. Of course, this is mostly going to be pushed by the EV market, which Turi will present more about later. We see that estimations for the year 2030 vary quite a bit. I have found numbers varying between 2,600 gigawatt hours up to 5,300 gigawatt hours. And I gave a similar talk back in 2019, and then the number for 2030 was around 1,000 gigawatt hours, meaning that this is an area where things are happening very fast, changing very fast. And the electrification is happening faster than expected. And if we're looking at the production of battery cells, that is also a market that is experiencing very fast changes and growth. The market is, of course, trying to adapt to the estimated future demand. We have now about 400 gigawatt hours of cell production capacity already, but we have another 1,600 announced for the future. And here as well, the numbers vary a bit. New locations and new plants are popping up. But the way it's looking now, we might start to see some shortcomings of battery cells in 2023 or 2024, depending on how fast these new gigafactories and new initiatives are able to ramp up. And if we look at where the production is taking place, it has been largely dominated by Asia, especially China. And that will continue to be the case. We see more activity in Europe ramping up, and towards 2030 will be maybe about 25% of the capacity in Europe. But we will still have over 50% of the capacity production in China, according to these reports. And if we're looking a bit more into detail about Europe and where we see the new initiatives, we know that there are quite a few interesting ones to follow now in Norway. And they are mostly consisting of new actors such as Northvolt in Sweden and Freyr and Morrow, new actors going into the battery production. But we also see more established manufacturers that are setting up new bases in Europe. And that is, for example, Tesla and Cathodes and Panasonic setting up mostly in Germany. And what we often see is that this is a strategic alliance between the battery producers and the car manufacturer, or also in some cases linking themselves up to a raw material supply. The current manufacturing capacity in Europe is around 26 gigawatt hours, but it's expected to increase to about 500 gigawatt hours by 2030. And here as well, a lot of changes, and I'm pretty certain that this map will be outdated within a year. I believe we all know how lithium-ion battery work and what the major components are. So I would like to focus the rest of the talk on the developments and the demands of the raw materials, and also looking at the trends for the cathode and the anode and the electrolytes, before I'll also briefly mention a bit about the path beyond the lithium-ion batteries. So if we're digging a bit more into the raw materials, we can focus on the most critical and the high volume elements shown here in the figure, and also mentioning, for example, lithium is the most important components in the batteries, I would say. Today, about 50% of the global market for lithium is used for lithium-ion batteries. There's been some discussions that we don't have a high enough supply of lithium, but it seems like the overall supply is okay, but there are instead some concerns or about the concentration where they are located that would give more accessibility issues. Cobalt certainly has some sustainability issues. We are using about 37% of all cobalt produced in batteries, and the production is concentrated around Congo, although the EU resources normally come from Russia. Due to these issues, there is a general trend to reduce the cobalt amount in the cathodes. When it comes to nickel, that is mostly used in other industries, mainly the stainless steel industry, but we are expecting an increase of the share that goes to lithium-ion batteries and reaching about 25% by 2030. And we also see a trend on going towards higher nickel content cathodes, pushing this number up. Carbon is, of course, the major component on the anode side, and graphite is being used in about 91% of the anodes on the market. And it's a mix out there between artificial graphite and also natural graphite. And if we're looking at the future needs of the raw materials, it's a bit complicated to estimate the exact numbers because it's depending on what type of battery chemistries that is used in the future. And but for all of these main components, it's expected to increase. This figure is already a bit outdated, but the trend remains the same. Lithium will for sure increase. And that's regardless of which type of chemistry that will prevail. Cobalt is also expected to increase, although we see a trend towards lowering the cobalt amount in the cathodes. Nickel will definitely increase, but especially this high purity class 1 type of cobalt nickel that is used in the lithium-ion batteries. And there's a large focus on the new gigafactories that are announced that they need to ramp up, but we also need to keep in mind that the mapping and the mining activities that will also need to ramp up at the same speed to avoid shortcomings. And there is often a longer path to establish new mines than to start a gigafactory. And the lithium-ion batteries, they're usually classified as the cathode material that is being used. So we have quite a large variation of cathode materials that can be used in lithium-ion batteries with their own pros and cons. So starting with the LCO, lithium cobalt oxide, that was the first commercialized cathode. It's been the leading cathode material in portable electronics, and it's been used in some of the smaller EVs, or the first EVs, but it's going to be reduced in the future use. LFP, lithium-ion iron phosphate, has a bit of a lower energy density, as can be seen in this figure here. Not that widely used in EVs today, has some niche markets in China. It's been considered to be very safe and sustainable. But there's a new update now from Tesla that's claiming that they will use more LFP in their next Chinese production. So LFP is now a bit uncertain. They might experience a boost if Tesla is going to produce or have LFP in their cathodes. NMC, lithium nickel manganese cobalt oxide, that's basically the preferred cathode for most EV batteries. It's here in the graph. It has a very good capacity, also lower cost than the LCO. There's a trend to change the composition of NMC to reduce the cobalt amount and to increase the nickel amount, meaning that NMC has been through a bit of a evolution. It started with NMC 111, meaning that nickel, cobalt, and manganese all had the same composition, towards NMC 532 and then 622, and now most producers are going for 811. But we also see the next ones trying to prepare for 955, so meaning 9.5.5. To even further reduce cobalt and increase nickel. This is expected to be on the market closer to 2030, as there's still a lot of research on this. Another cathode material is NCA, lithium nickel cobalt aluminium oxide. That's the version that's been found in Tesla cars. It has a quite or even higher capacity and a quite good calendar life. Then we have LMO, which is here. A bit lower capacity, but high power density, somewhat higher voltages. That is often used in a mix together with NMC. It's called a blend battery, where we can get both longer range and better power properties. A more recent development on the cathode side is the LNMO, lithium nickel manganese oxide. Has higher voltages, also quite manganese rich. It does still have some challenges with cycle life and thermal stability, but it's, for example, now on the roadmap of for example, Volkswagen as a more long-term strategy for cathodes. And here we have tried to summarize a bit the different scenarios and estimations that we see on the cathode chemistry towards 2030. We're mixing this into a figure here with reports from Bloomberg, Faraday Institute, and the report from SU. SU actually has two different scenarios, where the one has a more positive outlook on the LFP part, and the second one has a more outlook on NMC and NCA domination towards the future. So what is clear for all of them here is that we will see the nickel content in the cathodes increasing, and that can be either done by the NMC pathway, using more NMC cathodes and also higher nickel content in the NMC, or also using NCA cathodes. As mentioned, the LFP scenarios are a bit more uncertain. There might be a boost in the usage of LFP if some of the car manufacturers will use them in their normal EV cars as well, not just in some of the niche markets. But LMO and LCO, they are both expected to decrease in the future. And also for the NMC cathodes, everyone agreeing that they will increase and that we will go towards 811 and 955. On the anode side, we don't have that many options. There are basically two types of commercial anode chemistries, carbon-based and LTO. Carbon or graphite, that's been the main anode for over 20 years now, and that will also continue to be the main element in the foreseeable future, as it combines a good cycle life with a low cost. And LTO, that's considered more expensive than graphite, but it's been used in some of the niche markets where there's not so high requirements on the capacity, but where power density and high cycle life is a necessity. And of course, also silicon carbon composites is becoming more and more common. We have already quite some percentage of silicon oxide together with graphite in a few of the batteries, but we're seeing that this silicon content is increasing. And silicon is added to boost the capacity and still needs some issues with the expansion issue to be overcome before we can introduce it much more. And going into the electrolyte developments, there's a very large research focus on stable or working on replacing the commercial liquid electrolyte with a solid state electrolyte. That will, of course, give us more stability towards the higher voltage cathodes, which will again result in higher energy density. And it would also enable some of these more disruptive technologies, such as lithium metal. We have two types of solid electrolyte, that's the inorganic one and the polymer solid electrolytes. And at the moment, the polymer solid electrolyte, they're a bit more commercial, reached a higher TRL level than the inorganic one. But it is expected that the inorganic solid electrolyte will take over in the future due to their lower operating temperature and also higher energy and power densities. And we're seeing now that some of the OEMs, for example, Volkswagen and Toyota, they have a very defined roadmap towards solid state electrolytes. The question is when it will be implemented and to what market share they will take after 2025. There's still some issues that needs to be overcome in terms of connectivity and cycle life, also the contacting at the interface and stability between the electrode and the electrolyte. and also the reducing the thickness of these layers. When going from cell level to system level, there are also a few things to consider. There are now 3 different types of cells that we're looking at: pouch cell, this one here, prismatic cell, and cylindrical cell. And the market is not dominated by one cell type, so the different manufacturers are choosing whichever configuration that fits them best. But we see that when going from cell to system level, that's where we're adding the cooling system and the casing and the BMS. We are reducing the energy density, of course, and that varies quite a bit from the different cell systems. So for example, the cylindrical cell, it outperforms the prismatic and the pouch cell on the cell level, but it sees a quite drastic reduction on the system level. So that will make a big difference when we're designing the battery packs, and one reason why there's not one preferred solution. A few words about the possibilities beyond lithium-ion. We have, of course, a possibility of using lithium metal in the future, including lithium sulfur and lithium air. Sodium-ion, sodium batteries are also something that a lot of work is being done on. We have zinc and zinc air, and also redox flow batteries. But the key thing here is that many of them need the solid state electrolytes to be able to work. So they're sort of waiting for that to be fixed before they can be an actuality. And it's generally considered that the lithium-ion battery will outperform the close-to-market technologies in the next 10 to 20 years. Although many or some see the sodium-ion as a potential candidate if it can have some improvements on the safety side, and also depending a bit on the price reduction on the lithium-ion battery. So knowing what we know now about the raw material demand and the supply and the overall trends, I'll try and make a roadmap here for the future battery chemistries. So if we're starting with the midterm future, we know that carbon will still remain the main anode material, but we will get more introduction of the silicon into it. And NMC will remain as a main cathode material, with a trend towards increasing the nickel content. And we have NCA and LMNO as potential other cathode candidates. And the electrolyte will remain liquid in the near foreseeable future. More long-term goals is to start to see solid-state electrolytes, and also to be able to use lithium metal. So to try and close the loop, and also to come back to what the BATMAN project is focusing on, we have to consider both reuse and recycling. And reuse is, of course, the first step after the end of life. And the end of life of batteries is usually considered at around 70 or 80% of the original capacity in an EV. And that means that we could have a potential second life in a more low demanding application, such as stationary storage. And there is a lot of activity on second life of batteries now, also in Norway. And we have some pilots already established where we can, for example, combine stationary storage with PV panels. Currently, a lot of the batteries that are used in these pilots, they're not actual end-of-life batteries. They're batteries that have been discarded from the automotive industry for other reasons. So we still need a bit of research on the diagnostics and the evaluation of the state of health of the batteries, also looking more into safety concern and techno-economic assessment, and also LCA analysis of this second life business case. And if we're considering recycling, we're seeing that some materials, they might start to be dependent on recycling to meet future demands. This is a report on cobalt, where we have different scenarios on the future chemistry. So NCX, that stands for the most likely scenario where NMC and NCA will be the main cathodes. We have the LFP scenario, we're expecting a bit of a boost in the LFP usage. And then we have the lithium sulfur, lithium air scenario, where we're expecting that these more new technologies will have a significant share of the market in 2040. So if we're looking at the most likely, as of now, the NCX scenario, we see that we will look into scenarios of using cobalt where we're dependent on recycling in the future. And if we're also going more into the potential of recycling, this is a figure here looking at lithium and cobalt and nickel in the 2020s, 2030s, and 2040s, and what the potential for recycling would be. Again, I'm focusing on the NCX scenario, the most likely one with NMC and HCA cathodes. We see that for lithium, we could have almost 30% recycling, for cobalt, about 35, and also for nickel, almost 30% recycling rates in 2040s. This is again very dependent on these gray dots here, how much the second use will come into play. The second use of batteries will not necessarily reduce the recycling potential, but postpone them a bit in time, so that will come later. And this is where the BATMAN project is very relevant. We are, the main output of the project is to evaluate the recycling potential in Norway and focusing on the material demand and the recycling volumes by doing these material flow analysis. So I'll try and summarize briefly what I talked about. We're seeing that this increased need for raw material with estimated future battery demand, that means that we also need to ramp up the mining and the recycling efforts. And when it comes to the different chemistries, on the cathode side, NMC seen as the main cathode, where the overall trend is to reduce the cobalt and increase the nickel, and also having NCA and LMNO as possible alternatives. And on the anode side, we have graphite being the main component, but trying to introduce more silicon into the anode. And on the electrolyte side, for still some years to come, it will remain liquid, but then seeing solid state electrolyte time starting to gain some share of the market by 2025, 2030-ish. And with that, I just want to give thanks to some of my colleagues at IFE who have helped write this report and also prepare a presentation, and also with the great collaboration of the BATMAN project, giving valuable input and feedback into the report. And thank you for everyone for your attention.
And thank you, Hanne, for giving us a very valuable insight into the technologies of the and the developments that are happening. Just one comment before I leave it over to Erik to continue. Presentations, we will be able to share them. We will just have to again review that everything in the presentations can be shared, but there will be sort of a link that you will receive afterwards with the link to a presentation or a modified, slightly modified one. Also, I would like if you could just continue to use the chat function. There are some questions coming into the Q&A, but please use the chat function so everybody can see them if you're comfortable with that. So with that, I leave it also to Erik to talk about what is already shared on the screen, electrifying road transport in Norway. So Erik, up to you.
Thank you. So I am research leader for the research area Transport Technology and Environment at the Institute of Transport Economics. The Institute do research on all areas of transport. My research group mainly focuses on vehicles and vessels and the environmental impacts of using them, and my specific research area is electrification. Norway has become the world leader in passenger car electric vehicle adoption. In April, we had 13% battery electric cars and 5% plug-in hybrid cars in the fleet. And that means that the total numbers just passed 500,000 this last month, which incidentally happened at the same time in the UK, which is kind of a fun fact. In Norway, we have done this through having very ambitious climate policy targets and a large package of incentives. But we are also aided by the EU CO2 regulation for new cars, which is demanding 15% reduction of the average CO2 emission from new cars in 2025, and also light commercial vehicles and trucks, the larger trucks. And in 2030, the requirements will be even stricter, with minus 37.5% reduction for passenger cars and 30 to 31% for trucks and light commercial vehicles. And then in Norway, we have national targets which have been anchored to the national transport plan, which is renewed every 4 years. And here our target is to only sell zero emission passenger cars and small light commercial vehicles and city buses from 2025. The rest of the light commercial vehicles should be zero emission in 2030. And then the trucks, half of the trucks should be zero emission in 2030, and 75% of the long distance buses, which will be regional buses and coaches. So the EU has the requirements leads to a massive market introduction across Europe, which leads to large cost reductions for batteries and a massive rollout of vehicles in all segments. And then in Norway, we can then use our national policies to further support the zero emission vehicles. The targets I have highlighted here, they are areas that are now up for review in the European Union, and we can expect that even higher shares will be required for passenger cars and light commercial vehicles in 2030, but also that there will eventually be requirements also for the smaller trucks. Norway's national targets for the vehicles are at the bottom on this slide, and they have been sort of backcasted from the national overall targets, which are at the top, where we have the Paris Agreement, where we have our second national determined contribution is to reduce the emissions by minus 50 towards 55% in 2013 compared to 1990. And we had the previous Paris Agreement NDC, where we promised minus 40%. We have a climate law where it says we shall reach minus 40% in 2030. But we are currently not doing all that well. The 2019 emissions were almost as high as the 1990 emissions. And then the targets are split in two. You have the EU emission trading system sectors, where we have an agreement with the European Union. So our industries are part of the EU ETS, which is about half of the emissions. The other half are the sectors outside of the EU ETS, where we also have an agreement with the EU on an effort sharing basis, where our target is to reduce these emissions by 40% in 2030. And then you can go down to road transport, which are 35% of the emissions from the sectors outside of the EU ETS. And then you have what this actually means for the various sectors, so that you need to only sell zero emission vehicles in the passenger vehicle segment to be able to to reach these overall targets. If we look at current status, so the market share for passenger vehicles, the battery electric share was 54%. Of course, at the top of the policies, you have the EU CO2 regulation, which makes all these vehicles available to Norway. And then we have economic incentives, like the VAT exemption. We have the registration tax exemption. There are exemptions for the annual tax and the company car benefit tax. And all of these have been in use for a very long time. So we have a long history of developing the battery electric market. And then we also have incentives for the use of electric vehicles with the exemption from road tolls. And for those not familiar with Norway, I can tell you that road tolls are everywhere and they are quite expensive. So this is also a big incentive. We have reduced or free parking for EVs. They have had access to bus lanes since 2003, 2005. There are some rebates also on the main road ferries, which are sort of the coastal zones toll roads, you can say, from 2008. And we have support programs for infrastructure. Through these support programs, we have managed to build out fast chargers along all major roads across Norway the last 5 years. But there are also support for chargers, for instance, for people who live in flats and have common parking facilities. To the left here, you see the market shares for battery electric cars, which are the dark green color. You see we have several months with over 50% market share. And then you have the light green, which are the plug-in hybrids, and the yellow, which is regular hybrids. And then you have the internal combustion engine cars, which are the red in this chart. So how did this come about? Well, it makes a lot of economic sense for people to buy an electric car. They have the lowest total cost of ownership. They have had that since around 2012, 2015, depending on which segment you talk about. And if you look at to the left here, you have all the cost elements. And to the right, you have summed up for TCO without any taxes, and then the red bars on top are the taxes. So what you see is that what happens is that we tax battery electric cars very lightly. It's mainly electricity tax and VAT on some maintenance of the cars. And then we tax gasoline, diesel, and also plug-in hybrid cars quite high. And the overall result is that you save a lot of money by buying a battery electric car. And in this chart, the toll road incentive is included, but not free parking, reduced ferry rates, or the bus lane access. So it's actually even more attractive than what's shown here. And it's the same in all segments. And if I had shown a chart for the purchase price of battery electric cars are actually also now lower in all segments than for a similarly sized and equipped gasoline or diesel car. So in this chart, you see the month-by-month registration numbers for battery electric cars, which is the dark green, and plug-in hybrids added on top of that. Then you get to the light green color, and the red is the total number of first-time registrations, new and second-hand imported. So we're on the way to reaching the target, but it will require a continuing substantial incentive package. And it will also likely be necessary to have higher taxes on gasoline and diesel vehicles, as some incentives will be reduced over time. And Norway cannot ban the sales of gasoline and diesel cars because through the European Economic Agreement with the EU, we have accepted the four freedoms of the EU system. So, in which goods is one of the four freedoms. So, any item that's allowed to be sold in the EU cannot be banned in Norway. With the EU CO2 regulation, we see two effects. One is that there is a rapid increase in available models in all segments from all brands. So it's going to go up from about 40 battery electric car models in this year, and some tens of plug-in hybrids, and up to 180 battery electric vehicle models and 110 plug-in hybrid models in 2025. And the second effect of the EU CO2 regulation is that earlier battery electric vehicle generations have come in sort of limited volumes. It has been long queues of people wanting to buy one. And this volume limitation is now more or less lifted. All these cars are now that comes on the market now are designed for high volumes. One of the biggest things that happened last year was actually that Europe is slowly catching up with Norway, and there was a huge increase in the electric vehicle adoption across Europe. Norway is still number 4 when it comes to absolute numbers of EVs. And of course, our combined market share for battery electric and plug-in hybrid cars is by far the highest of any other countries, but it's increasing a lot also in the large countries in Europe. So I would say that 2020 was the breakthrough year for battery electric and plug-in hybrid cars across Europe. And when you look at these numbers here, you will see that Nordic countries are the forerunners, followed by the Western Europe. And then the sales are much slower in Southern Europe and in particular in Eastern Europe. When we come to the battery electric light commercial vehicles, they had a market share last year of 8.5%. But during 2020, the sales suddenly started to take off, and this has into this year. And there are two reasons for this. The one is that we have support from Enova, which is a public agency which is tasked with supporting new technologies to reduce greenhouse gas emissions. But also a huge increase in the availability of more attractive battery electric light commercial vehicles, which I will show on the next slide. So of course, the incentives are more or less the same for light commercial vehicles, but the VAT exemption doesn't work for commercial vehicles because a company can deduct the VAT anyhow, so it has zero value. So the incentives are smaller for commercial vehicles than it is for passenger cars. And that you also see by the scale difference. So the right-hand side scale is for the battery electric commercial vehicles, which is the red color, and the left graph is for the passenger cars. So you can see that the market has been 5 times higher for battery electric cars and for the market share for battery electric cars and for battery electric light commercial vehicles. But now this year the market for light commercial vehicles is starting to take off. There is also, in addition to the fast chargers along major roads, and of course on commercial terms, they also build them out in cities. They also have advantages from chargers in parking areas for flats, because many craftsmen, for instance, take their vans back home in the evening, and then they need to charge them. And there has also been some possibilities to get support for chargers at depots, and Oslo municipality also is putting up some chargers which are dedicated to commercial vehicle use. We asked in 2017, 2016, the users of the first battery electric light commercial vehicles, what type of vehicles they need, what characteristics they need, and they say they need fast charging, payload as for diesel, they need a tow hook, a wide selection of models, and a range all year of 200 kilometers, and they also need medium and large light commercial vehicles. With the latest generation coming now, we see that they meet all the needs for the smallest commercial vehicles and for the medium ones, whereas the large ones are still lacking on charge speed and also range. And none of these can be delivered with four-wheel drive, which is also a requirement that many users of these vehicles have. These types of vehicles have had the lowest total cost of ownership since about 2015, 2017. But it's not as beneficial as for the passenger cars. They get on the positive side because they drive longer distances per year than a typical passenger car. So we save more on the energy cost, for instance. And also here, it's the taxing of the diesel vehicles that is the clue to the competitiveness of the battery electric cars. Buses, there is a rapid development for city buses in all sizes and classes. You can now get them available from several suppliers. Battery capacity has increased tremendously. Now you can get batteries up to 480 kilowatt hour in 12 meters buses and 640 kilowatt hour in articulated buses. And there are currently 400 buses in use in Norway. Coaches, you can also find a few coaches available, and they have even, some of them, even larger batteries. There are about 50 in use in Norway currently, used for cruise traffic, for instance, to transport cruise tourists from cruise harbors to attractions nearby. When it comes to the battery electric trucks, this is just getting started in Norway. There are 65 in use. Schenker is the biggest user, followed by ASKO, and then there are DNB Bank is a leasing company, but all of the users have very few of these vehicles so far. So it's mainly demonstration and testing purposes. The infrastructure, public infrastructure, doesn't exist, so they charge in the depots. The cost of buying one of these cars is currently at least 2 times that of diesel, often 3 times. But we now see also here a huge interest from the vehicle producers due to the EU CO2 regulation. There are some incentives available from Enova for purchase support. And the road toll exemption is a very important incentive for these heavy duty cars because the road tolls are very expensive for large vehicles. Here you see an overview of all the vehicles that are types of vehicles that are coming. There are battery electric vehicles coming in all segments, below 16 tons, 16 to 80 tons, 27 tons, above 27 tons, and even for long haul next year. There will be vehicles coming, and they get also much larger batteries than the first generation of rebuilt trucks had. And that's another difference we see in this market, is that we now move away from refurbished diesel vehicles to series production by the traditional truck producers. And they have professional service programs. So you get the same support and service for these battery electric cars as you get for diesel vehicles. So they are now ready for professional use, although they are still a bit expensive. And there are some competing technologies, hydrogen, that is for now only demo projects, and there is no real industrialization possible or planned for until after 2025. There's currently one refueling station in Norway, which is company internal at ASKO, which is a grocery distributor located in Trondheim. And the other alternative is biogas, which is also semi-available. We have 2 filling stations currently. That is a limited resource, but it could be used for part of the market. So if we look at the status of the technology and how it meets user needs, the market situation, infrastructure build out, cost of the vehicles with incentives, the policies available and the knowledge, we see that there is still a lot to do on when it comes to the heavy duty trucks and coaches, long distance buses. But all the others are in good progress, and the biggest remaining issue is maybe infrastructure for all types of vehicles and costs for the heaviest vehicles. So that was my presentation.
Thank you very much, Erik. We still have some time for questions, and it's first of all, I would just like to thank the 2 presenters for a very valuable insight into the 2 different areas. First, let's see if we can just have some of the questions. The first one is, as I see it, to Hanne. Will we see systems with multiple chemistries emerging? And I think as such it is mixed chemistries, but and you presented some of it. And do you have a comment to that?
Yes, I can maybe highlight. I presented that the LMO, lithium manganese oxide, is quite often used in a combination with NMC. That's the most typical blend or mix that we see. It's used in both high power tools, some EVs, if I remember correctly, Nissan Leaf is one example. So that is for sure one type of blend, and I'm sure there are others to come as well.
Thank you. Next question is for Erik, and it's related, and I think if somebody has calculated it, it may be you. Have you ever calculated how much the incentives all combined in Norway per car per car? Yeah.
On a per car basis, no, but it is well, the incentives are mainly causing a loss of income for the government or the toll road company or the ferry company. But if you calculate that income loss, it would be above 10 billion NOK, Norwegian kroner each year.
Yeah.
I don't have remember the exact number, but
no, and for non-Norwegians, I think that the one thing which is the main initiative, as you said, it's the cars are initially so heavily taxed. So when you take that away, then it starts to be very competitive. So, and as the prices for cars change, I'm sure that there will be a balance also of how the taxes apply, so that it still will make sense to buy an electric car. There is also another question, if you know if there is any incentives for charging infrastructure for buses in towns.
Buses in towns, well, you can get support from Enova, but you have to install and apply for it before you put out the tender for the bus service. So there are some there you have to make sure that you follow and you do it in in the right way. But there are support programs at Enova for this type of infrastructure.
Okay, thank you. Then there is and it's a little bit long question. I'll read it out. It's for you, Hanne. Could you add further insights related to the access to lithium? What are typically related as the most concerning aspects in the literatures you engage with? The rates and speed of investments into new extraction sites, or the small number of countries where large quantities are extracted, limited to the number of owners holding access to rights, and the concentration of ownerships and access in Asia? It's a long question, but I think you get it.
Yes, I'm not sure if I can pinpoint one of them as to be the most concerning. I think these are all very valid concerns. Lithium being mostly accessible in South America would provide some access limitations to other countries. And of course, there are some companies and owners that have a large fraction of these sites. And I think we have discussed this in the BATMAN context a few times, that this is a reason for concern in Europe, and also why we're looking more into recycling to be able to control more of the material flow within Europe and also within Norway. So again, I'm not sure if I can pinpoint one of these concerns to be the most pressing one, but they're all very valid concerns with the geographical concentration of lithium sites.
Yeah. No, I think that we don't have any more questions, so we will just round it up now. But as far as I saw for the latest presentation from the European Battery Alliance, we are well on the way in building capacity, but where we are actually not building enough is on the raw materials. So that could absolutely be a limiting factor as more and more countries implement more and more activities to ensure that we have electrification of the vehicles. So I think we leave it with that. Thank you very much, everyone, for participating, and special thanks to Hanne and Erik for giving valuable insights. And I wish you a nice afternoon. Goodbye.
Bye.